Welcome to the first learning outcome. Here, we're looking at what makes a research project trustworthy, the ideas of integrity and quality, and how validity, reliability, and ethics fit into a computing project. A research project is really only as trustworthy as the way you carried it out. Integrity means being honest and open at every stage, and quality means your work genuinely answers the question with evidence others could check. Think about a usability survey that's badly worded. It can quietly push you towards the wrong conclusion. So across this outcome, we build three ideas: validity, reliability, and ethics. And it's good methods, not just tidy results, that make a project credible. So what do we actually mean by quality? In research, it comes down to how far your findings can be trusted and reused by someone else. Two technical ideas sit underneath it: validity, which asks whether you're really measuring what you set out to measure, and reliability, which asks whether you'd get the same result again. Add ethics to protect the people and the data, and together, those three decide whether a project is fit to be submitted. Let's put names to the three concepts you'll meet throughout. Validity is the extent to which a method actually tests what it claims to test. Reliability is about consistency. The same method repeated should give you the same answer. And ethics is the set of moral rules that keep the work honest and protect your participants and their data. There's a classic target analogy that makes this stick. Imagine the bullseye is the true value you're chasing. Validity means your shots land on target, and reliability means they're tightly grouped together. You can actually be reliable, but not valid. A stopwatch, you always start a moment late, gives lovely consistent boot times that are all wrong. What you're aiming for is both accurate and repeatable. Validity comes in a few flavors worth knowing. Internal validity is about a clean design, so the result really is caused by what you think and not some hidden factor. External validity is whether it generalizes beyond your one machine or small sample. Construct validity asks whether your measure genuinely captures the concept. Does a survey question about ease of use really measure ease of use? And ecological validity checks that the test reflects real conditions. Testing an app only on a high-end PC tells you little about a typical student laptop. In a computing project, reliability really means repeatability. A good habit is test-retest. Run the same benchmark several times and check the numbers land close together and keep the conditions fixed. Same hardware, same software version, same background load. Then report an average of several runs rather than one lucky measurement. Measuring an operating system's boot time once tells you very little. The mean of 10 cold boots on the same laptop is far stronger. It helps to picture validity, reliability, and ethics as three pillars holding up your project. Weaken anyone, and the whole thing starts to wobble. Validity keeps your findings accurate, reliability keeps them consistent, and ethics keeps the process honest and safe. When an examiner reads your methodology, they're looking for evidence of all three. Let's walk through the first few ethical principles. Informed consent means people agree to take part after you've told them the aims, what's involved, and that they can withdraw. Confidentiality means whatever they share stays private and isn't published in a way that identifies them. And anonymity goes a step further. No name or identifier is attached to the data at all, so an individual simply can't be recognized. There's a second cluster of principles that matter just as much. Avoid harm, which includes protecting people from stress or embarrassment and protecting their devices and data. Follow data protection law under GDPR by collecting only what you need and deleting it afterwards. Design fair questions and samples to avoid bias and cite every source to avoid plagiarism. Passing off someone's code as your own breaks academic integrity. And above all, honesty. Never invent, tweak, or quietly hide data to make your findings look better. Let's set validity and reliability side by side. Validity asks, is it accurate, on target? Reliability asks, is it consistent, repeatable? For a survey, validity is whether it measures real usability, while reliability is whether repeated benchmark runs agree. The main threat to validity is a wrong or biased measure, and you fix it by piloting. The main threat to reliability is changing conditions, and you fix it by standardizing and averaging many runs. Here's a very concrete example. A student surveys classmates about a new note-taking app and asks, "This app is amazing. Do you agree?" That leading wording nudges everyone towards yes, which is a threat to construct validity, and only asking friends who already like it is a biased sample, a threat to external validity. A neutral question works far better, something like how easy was the app to use on a 1 to 5 scale, put to a mix of users across different abilities and devices. Small design choices like these decide whether anyone can trust the findings. Now, a reliability example. A learner compares two sorting algorithms by timing how long each takes to sort 100,000 records. Run each one just once, and the figure is at the mercy of whatever else the machine was doing. Run each 20 times with other apps closed and average the results, and it's far more trustworthy. Reporting the mean alongside the spread, the standard deviation shows how consistent the runs were, and keeping the same machine, dataset, and language means another student could repeat it and expect similar numbers. So, how do you build validity in from the start? Begin with a clear research question so every measure ties back to the aim, and pilot your surveys and benchmarks on a few people first, then fix anything confusing or leading. Choose measures that genuinely fit the concept. Task completion time is a fair measure of efficiency, and widen your sample or test across several devices so the results generalize. And write your design choices into the methodology so the reader can judge validity for themselves. Reliability is built through discipline. Standardize your procedure and write it down as a repeatable set of steps. Control the variables, same hardware, operating system version, dataset, network and power mode, and repeat each measurement several times, reporting the average. Use consistent instruments too, the same timing tool and the same scale on every survey question. And keep your raw data and scripts, because if a reader can't repeat your method, they've no reason to trust your numbers. Ethics isn't a one-off box you tick at the start. It runs through the whole project. You give participants an information sheet and gain their informed consent. Then you anonymize responses and store them securely under GDPR. You use the data fairly and report it honestly, and once it's no longer needed, you delete the personal data. That whole life cycle, from consent to disposal, is what ethical practice looks like. It helps to run through a checklist in 2 halves. Before you collect anything, ask whether you've explained the aims, gained written consent, kept your questions neutral, collected only the data you actually need, and got your tutor's approval. Then during and after, check responses are anonymized. Data is stored securely behind a password. Every source is credited. Results are reported honestly, and personal data will be deleted when you're finished. Ticking these off genuinely protects both you and your participants. Let's apply that checklist to a real study. A student evaluating whether an AI writing assistant helps peers plan essays using a short task and a survey. For consent, each volunteer is told the aim, and that taking part is optional and can stop at any time. For confidentiality, responses are labeled P1, P2, P3 rather than by name. Under GDPR, the results sit in one password-protected file and are deleted after grading, and for honesty, the student reports that some users dislike the tool, not just the fans. And any AI-generated text used in the report is quoted and acknowledged, never passed off as their own. Gaining informed consent really has 4 steps. First, you inform, handing over a plain language sheet covering the aims, what's involved, and how long it takes. Then you explain their rights, that taking part is voluntary and they can withdraw without penalty. Next, you actually obtain consent, a signature, or a ticked online box before anything starts. And finally, you record and store that consent securely, kept separate from the anonymized data. Any personal data you collect falls under the UK GDPR and the Data Protection Act 2018. The key ideas are data minimization. Only collect what the question needs and avoid names or emails where you can. Security. Keep data on encrypted or password-protected storage rather than a loose USB stick. And purpose and retention. Use the data only for the stated research and delete it once the project's marked. The Information Commissioner's Office publishes really plain guidance on all of this on its website. A handful of risks come up again and again, and each has a simple fix. Leading questions produce biased data, so pilot and reword them to be neutral. A single benchmark run is unreliable, so repeat and average, and storing names risks a GDPR breach, so anonymize and encrypt. Uncredited sources amount to plagiarism, so cite everything in Harvard style, and cherry-picking data is simply dishonest, so report all your results, including the negative ones. Academic integrity just means your work is honest, original, and properly credited. And plagiarism is presenting someone else's words, ideas, code, or figures as your own. You avoid it by citing every source in the text and listing it in a Harvard reference list, quoting directly when you use exact words and paraphrasing in your own words with a citation otherwise. And this applies to code too. Reusing something from a tutorial or Stack Overflow has to be acknowledged just like text. Tools like Turnitin will check your submission, but the real safeguard is careful referencing built in as a habit. Let's pull this outcome together. Quality research rests on 3 pillars: validity for accuracy, reliability for consistency, and ethics for honest, safe conduct. Validity asks whether you're measuring the right thing, and reliability asks whether repeating the method gives the same result, while ethical practice covers consent, confidentiality, avoiding harm, GDPR, avoiding bias, and avoiding plagiarism. You build validity by piloting and aligning your measures to the aim, reliability by standardizing and averaging, and ethics runs right through, from consent and secure storage to honest reporting and deleting data at the end. And that brings us to the end of the first outcome. If you'd like to go further, there are some excellent guides. Dawson's projects in computing and IT and Oates on researching information systems are both a great start, and Braun and Clark's paper is the go-to on thematic analysis. For the ethics and data side, the Information Commissioner's Office Guide to GDPR and the BCS Code of Conduct are well worth a look, and cite them right will keep your Harvard referencing on track. You'll find the ebooks, journals, and open datasets for this unit on Moodle, so do dip into them as you plan your own project.